Hello everyone, how are you? I hope you all are fine at your places. So today we will see the CPU OS simulator, the practical which you have in your OS last practicals. So here for we have opened this OS CPU OS simulator. When we open this CPU OS simulator, you can see there are so many windows, so many options, buttons are there. But you might not need that all for your practical sessions. But if you are exploring this option, then it will be good for your learning. And it is having all the CPU based execution, so it will help you in learning of your COA subject as well and processes as well. So first we will see, this is my first window of your CPU OS simulator. So here you can see this is the CPU instructions in memory, that is RAM. So whatever code you want to execute, you have to load your code here. So either you can write it there or you can have the already written pre-written code, you can upload it there. Then we have this one option here, cache pipeline and execution unit. So while executing a program, how your program, each single line is executing. So that you can see with the help of this execution unit. So as everyone is aware, whenever a program is executed, so it's line by line instruction will be fetched to your CPU. It will be decoded and it will be executed after decoding. So these are the steps mentioned here: one fetch, two decode, and three execute. So according to your instruction, the instruction will be fetched here from assembly language. It is decoded according to the opcode of assembly language, and it will have this operand one, operand two if it is there. And then while execution, you can see here, this is your program counter. These are all the CPU registers. This is program counter, stack pointer, base registers, and serial registers. Then these registers are having this flag. So this is zero flag, this is negative flag, and this is overflow flag. So when we get any errors into your program execution, you might have seen that the buffer overflow error is there. So that you can see with the help of this OV flag is there. Then this is instruction register, memory address register, and memory data register. So whatever the values are there into these registers, this you can see one line by line execution with the help of these register status. Okay. And here we have this general purpose CPU registers. So you can see there are total 32, 0 to 31. Total 32 registers are there associated with CPU, and these registers, by default these values are 0, but when you load your program according to your program execution, these registers will have these values. Then this is program stack. What is a program stack? How many variables are there? What is their position? What is the value of that particular program variable? That all will be listed here. This is your program list. How many programs you have loaded into your memory currently? So right now we haven't loaded any program here. So for starting our program, we have to first load our program. So while loading a program, first we need to compile it. So you have to go here to this compiler. Here we have option of compiler, input, output, interrupts, OS, virtual OS, etc. Out of these, for our practicals, we will be using only this compiler and OS. So first go to compiler. Here, this is your program source, that is input. This is your compiler progress, and this is the total area of assembly language code. So first I will load a program. This program I have already shared with you, the loop test.txt. So this is my loop test program. So I'm opening it. This is my program. So program loop test, I equal to 0 for n equal to 0 to 50, I equal to I plus 1. Next. So it will loop around 50 times for your for value of n, and then end. So here I need to compile it. So go to this compile section and compile. See, now this program has been compiled, and automatically this program has been converted to the assembly language code. So for every line of execution, these are the some assembly language codes are written here. I hope you must have knowledge about this assembly language program because of the COA and basic structure of OS. So here your first line is, this is your logical address, CPU and instruction, binary code, line on which line the program this is written in our program, and then the comment, that is what is this CPU instruction is doing here. So if we see, This is a compile process. So everyone is aware about whenever a program is compiled. So what happens in compilation of a program? First, there will be a tokenizing of your source elements. Lexical analysis means how many tokens are there which are identified as keyword, or how many words are there into your program, that will be counted and taken into consideration. So this is your program written in a single line, or here total 18 tokens are found here. Now after that, constructing the symbol table. So symbol table means what? How many symbols are written into your program? So that can be symbol, that can be keyword, etc. So here, checking source syntax. So this is syntax analysis, whether your syntax is correct or not. So that will be checked according to syntax analysis. So here, for every line, it will scan for whether it is properly written or not. So it is scanning for keyword program. So program is a keyword which is found into the library. Then keyword equals to. So equal to is there. Then assignment statement, for statement, keyword equal to, assignment statement, etc. This is all written for this found. This is equal to assignment statement, for, and next. So after that, next and end. So similar way, whatever the program you have written, it will be compiled. Then after compilation, after syntactical analysis, it will be generating the assembly language code, which we can see here. So here we are assuming that our logical address is 0. So our program is starting at 0th location. So at 0, it is the program is having move #0, R03. #0 is your numerical value which is you are passing, and R03 is your regular register. So here this I equal to 0. So this 0 value, we will be copying it to a register. Then move R03 to R01. So we are moving it to R03 to R01. And again, similarly, we have taken into consideration for all the assignment statements. Then comparing this value R04, R02. Then this JGT is a jump instruction, CMP is a compare instruction, add is addition, move is moving data from one register to another register. Then halt, that is for final ending of your program. So now this is the all assembly language code which is automatically generated. Now we have to load this assembly language code into your RAM, that is main memory. So you have to go here. This is a button, load in memory. So here we have option that either we are selecting the starting address as 0, or we want to take it some another address. So here our program code is having 69 bytes. 69 byte code is a program size. And here select CPU. So suppose we have only one CPU here, so that is CPU 0 is written here. Then base register, by default the option is -1, so that the next value will be starting from the 0th location. But if you want to change this location, you can untick it and change this value. But for this program, we are not setting any extra specification to this program execution. We are just continuing with the default formats. So go to this load in memory. So now we have got the message, code successfully loaded in memory. So say okay. Now this is your code. This is which is in the memory right now. This is your program name which is in the memory right now. Now if we want to see how these program instructions are executing. So this is my first stack pointer. So this is my program counter which is at 0. You can see this PC equal to 0. Okay. So now this is my code which I want to execute. So first option is fetch. In this execution unit, go to fetch. So this first line, move #0 R03 is loaded here. Instruction is move #0 R03. Then decode it. So while decoding, we have got the instruction as opcode is MOV, move, and these are your operands. Then execute. Now before execution, you can see here, this is your instruction register, this is your memory address which is 0, that program counter was at 0, and MDR, memory data. So what is there in data? This 0 and #0 and R03. Now you have to execute this. So when we execute it, automatically you have seen here R03's value has been changed to 0. Now, by default, it was 0. That is why we didn't recognize it, but it is set to 0 now. Now again for the second line we want to execute it. So again you have to fetch the code. So now you can see the program counter is at 6, which is this line, second line, E06. And this is your stack pointer 8096, which is written, which is shown in as a arrow here. Okay. Then now this is my second line. Again, I have to decode it. You can see R03 is my operand 1, which is value having 0, and operand 2 is R01, which is value by default is 0. So then execute it. So again, you can see here, this value from R03 to R01 has been shifted. Now your cursor automatically came to this R01. Now again for third line, if I am fetching the instruction, it is having the move #0 and R04. So this is when we decode it, automatically my operand 1 is 0 and operand 2 is R04, which is value is previously 0, and execute it. So now see, automatically your cursor has been gone to R04. So automatically, once instruction by instruction, if you want to see the execution, you can see it with the help of this fetch, decode and execute instructions in execution unit, or you can execute entire program at once. Okay. Now we have to go to this OS section for our process execution. So this is the execution unit for operating system. Now in operating system, we have to create new processes. So my basic one process is in CPU right now, which is loop test. Now inside this loop test, I want to create some more processes with my with their lifetime according to my requirement, and we can set when the process comes to the scheduler at time 0 or at later times. So here, this is my program list. You can see here, this is my main program. Here, process name, priority you can set, pages, how many pages it will require for execution you can set here. This is the cascading effect. If parent dies, children dies. You can untick it if you don't want to do this. Then process lifetime. So how much time the process will be there in execution, that you can set here. Either you can set this in terms of ticks or seconds, depending upon your situation. Then arrival delay. So delayed process. So we can set any of the delay process after 1 second, after 5 seconds, 10 seconds, whatever. After some time the process is coming to the execution, that you can set here. And again for this same ticks or second, you have to choose. Make sure you are choosing any one, either with the time ticks or with the seconds. Otherwise you will get confused while execution. So first, here we will be creating some processes. Now suppose I am creating my process P1, which is having lifetime of 3 and which is coming after 1 second or one time tick. Okay, and create new process. So when I have created this process, you can see at the left side, we have here three sections. This is running processes, this is ready processes, and this is waiting processes. So since I have created one process and that process main parent process is already in the RAM, the loop test program, which is already in the RAM. So that is why my process is in a ready state. But it will be ready after one tick of time, which I have set here. So that is why it is in a waiting ready, but it will coming after some time. Then process 2, suppose I want to create a process 2 having the same priority, same pages according to my first one, and lifetime I'm setting it here as 4, and it is arriving at 0th time. So there is no delayed process suppose, and create new process. So this is, you can see here in ready processes, my process 2 has been come here because it is arrived at 0th second. Then again process P3 I will be creating, which is having lifetime of 2 and which is coming after 1 second. So this is arrival delay is 1 second, and create new process. Okay. Now here we can see that these processes are created. Now we want to execute it. But for execution, you must be sure that in this OS control, we have the start button for execution and step for coming to the next step. But here we want to see the animation video. So that is why we will be making this time tick, the speed, CPU speed as slow. and we are using only single CPU. So that is why I use single CPU for execution. We can choose any multiple CPUs as well, called multiprocessor environment. Now we are using round robin algorithm here. And in round robin algorithm, suppose I am choosing the time quantum in terms of ticks, which is of 1 tick. Okay. So here I have set this as preemptive one. Now what happens if we are setting round robin as non-preemptive one? It will work like FCFS. So I don't want to work like FCFS. I want to work like round robin, which is preemptive one after execution of particular time quantum. A process which will happen and another process will come for the execution. So that is why we are taking this preemptive one. Now after this is one option as static. So static and dynamic. These two options are there. This means at time of running, you can add some process or you cannot add it depending on the situation. So here, first I'm doing this start. So as soon as you do this start, you have to see various views of operating system. Means how many programs are there in memory, what is the PCB of particular process, what is the CPU utilization of the processes, or you can see how this process is executing, means how the process is coming to ready state, ready to running state, running to executed state, or in waiting state. So that we all have to see. But since the time quantums we have defined for these processes are so small, we will be making the CPU speed as very slow. And as soon as we are starting the process, we are going to this views tab. In this view tab, we have a view process steps. So that we will click here. So we will first start the process. So start, go to view and view process states. So here you can see these are the total ready state. These are all processes which are in a ready state, and this is the CPU 0 which is executing particular process. So according to round robin algorithm, whatever is your process scheduler, it's scheduling the processes that you can see here. So process 1 has been finished, process 2 will finish, and now entire processes are finished. So if you want to see the schedule of the processes, how they have executed, when they have executed, when they have come to the ready queue and gone, so you can have this view log. So when in this view log, you can have this example. First P2 process is loaded into memory into the ready queue because P2 process started at 0th time. Then new scheduler session started. Scheduling scheme is round robin static priority, which is where we have set the same priority for all, and we are using the preemptive session, and we have used the time slot as 1 tick. Then memory allocation policy is first fit. Now what is this first fit? If you have already done these first fit base fit algorithms, you might have understand what is this first fit memory allocation policy. Whenever your program is coming to the memory for execution, so whatever program will need some space to occupy, and it will find the space whichever is same or greater than the required space of the process, that will be allocated to that particular process. So in the first bit algorithm, we will be finding the first space which is sufficient for a program to allocate. So this is the first bit algorithm. Then it is done automatically by your operating system in your CPU simulator. Then after this P2 is gone from ready state to running state for execution, it has executed for one time quantum, and after that again P1 process is loaded, P3 process is loaded, and P2 which was in running state, it is going from running to ready state. And after P2, P1 process was there, it has come at time 1. So P1 process was gone from ready state to running state. Again it will execute for one time quantum, it will come back from running to ready state, and it will give chance for process P3. So P3 will go to running to ready state. After running it, again it will come to the ready state and give chance for the next available process. So similar way, this will keeps on going until all process executions are finished. So this you can see here. This is the all system log for all the processes. Now first process P3 has finished because P3's time period we have set very small. So P3 needed tick count as 2, means 2 time quantum process P3 has finished. So process P3 has elapsed time of this much. Total, this is your elapsed, that is turnaround time. This is your total waiting time for execution of the process, and this is your burst time of the process. Then after this, memory swap count is 0 because it has come only once into your CPU. Then Your process P2 was remaining for execution, so P2 P1 executed completely, and P1 has finished because P1 time slot was less than P2. So P1 P1 statistics are all shown here. Similar way, last at the last you can see this is the statistics for P2. So similar way you can see all the statistics for all the processes which are executed into your CPU. If there are some errors, you can see errors here also, but now for this execution we have not got any errors. Here we have option of log detail in view. So this is a low level log detail, mean every time what is happening that we can see here. If you want to see the high level, so okay, let it be. So we will close it. I hope you all can execute various types of processes here with the help of this round robin shortage of first come first serve basis. So here we have taken example of this. This was my example process arrival time and their lifetime, and according to that what is the round robin schedule for preemptive processes. So this is my schedule which we have executed. So similar way you can choose any of your example, you can choose any algorithm and execute it and try to do it. Okay. If you have any doubts, please ask me. Thank you. All the best.